In this section, we're going to be looking at the exponential function and how to take the derivative of that exponential function. The good news is that it's pretty easy. So when you just take the derivative of the exponential function, and this exponential function is e to the x power, when you take the derivative of e to the x, you just get back e to the x. You can't make it any easier than that. However, how can you make it harder is that you're not always going to have x as the exponent, and so we're going to have to use that chain rule. Your book writes it in terms of f of x. If you have e raised to a function of x, then you get back that e to the, that should be f of x, multiplied by the derivative of the exponent. I like to use a u substitution, and it says if you have e to the u power, you get back e to the u power times the derivative of u. In other words, you always get back the same exponential function you started out with, multiplied by the derivative of the exponent. That's what we're going to concentrate on in this lesson. So let's just start out with some really easy examples. These are the odd ones from the book. And so on the number 1, f of x equals e to the 3x. That's your exponent. And so our derivative is the original function, that's e to the u, times the derivative of the exponent, which is just 3. All right. So if we have g of t equals e to the negative t, again, there's our exponent. So we want to write down the problem just like it is, e to the negative t, that's e to the u, times the derivative of the exponent, which would be negative 1. And there would be our derivative. All right, now let's mix up some x's with e's. All right, so we have this function. All right, the derivative of just e to the x is e to the x. The derivative of x is just 1. Now this last one, notice it's a product, so we're going to have to use the product rule. Okay, do y'all remember the product rule? Right, we could come over here and write the two functions like this, and then take the derivative, so that'd be 3x squared, and the derivative of e to the x is just e to the x. Remember, we multiply and add those, and so the derivative is going to be x cubed e to the x plus 3x squared e to the x. Right, yes, now it's going to start getting a little more complicated. So here we're going to have to use the quotient rule. Right, that quotient rule says to take the bottom times the derivative of the top. Okay, we're just going to leave that constant there, and the derivative of e to the x is e to the x. So the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Those are unlike terms because of the x, and that's our derivative. Right, on number 11, I have a couple of different ways to do it, but I think the easiest way would be to go ahead and distribute that 3. And so to take the derivative, we're going to leave the constant alone. The derivative of e to the x is just e to the x. Leave your constant alone. Take the original function, e to the x, and then we need to take the derivative of negative x, which of course is negative 1. If you notice, we almost got back the exact same function. The only difference we have is the minus sign. All right? And I think you get the idea. Just because they're e's really doesn't make it any harder. Let's look at some of these. All right, number 17. All right, so the derivative, keep the same exact function but then you need to take the derivative of the exponents. That's going to be negative 2x. So it looks harder, but it really isn't. Okay, so number 19. All right, so we have the derivative is the exact same function times the derivative of the exponent. Now, that looks a little bit more complicated. So that exponent is really negative 1 x to the negative 1 power. So I'm just going to call that, let's call that u. And so the derivative of that would be positive 1, because I'd bring that down in front and subtract 1 from the exponent. So my derivative is 3e to the negative 1 over x times 1 over x squared, bringing that to the denominator. Just rewriting that a little bit prettier. So sometimes I think it's necessary to come and do the derivative of that numerator separately. All right, so we're going to use the chain rule, which means I've got to take the derivative. So put that 25 in front, subtract 1 from the exponent, and then take the derivative of the inside part. The derivative of e to the x is e to the x. The derivative of 1 is 0. So my final answer is that. Okay, so we have some more complicated expressions. Number 23 is similar to that other one, where I might go ahead and write that as u as x to the 1/2, and then take the derivative like that. But let's look at number 25. I've got the product again. Truthfully, I think I could distribute that and then not have to use the product rule. So that's one option. Let's try that. So if I actually distribute that, that's going to be x e to the 3x plus 2 minus e to the 3x plus 2. Not using the product rule. Well, you know what? I'm going to have to use the product rule there anyway. Right? So let's take the derivative. So the product says the first times the derivative of the second. The derivative of that is 3. All right, so let's just say that one more time. Took the first one, taking the derivative of all of that, so you get the original times the derivative of that exponent. But that's not the rest of the product rule, plus the second times the derivative of the first. All right, then I have to take the derivative of that part, so I'm going to say minus e to the 3x plus 2 times the derivative of the exponent. Putting that together, these are like terms, so I could collect like terms and put it together like that. Now that's one way to work the problem. Another way is that we could have used the product rule of this multiplied by that. We would have come up with the same answer. Might have looked a little bit differently, but it's the same answer. Number 27, definitely going to have to use that quotient rule. So our quotient rule says to take the bottom times the derivative of the top. The derivative of e to the x is e to the x. The derivative of negative 1 is 0. So the bottom times the derivative of the top minus the top, use those parentheses, times the derivative of the bottom, all divided by the bottom squared. So let's see, I could multiply that out. I don't think I have anything alike. Let's see, I'm going to factor out an e to the x. So that leaves me e to the x plus 1 minus e to the x minus 1. At this point, I'm just simplifying. I'm going to distribute that minus. Notice, let's see, those cancel out, and so now I have 2 e to the x over e to the x plus 1 squared. So this was the derivative. This is the simplified answer. All right, now they're asking us to take the second derivative. That just means take the derivative twice. So let's go through that. All right, we'll keep the original function times the derivative of the exponent. The original function times the derivative of the exponent, and that's my first derivative. Second derivative, let's go through the same thing. Original function times the derivative of the exponent. Sometimes taking the derivative of the exponential function is so easy, it's hard because you're like, did I take the derivative? And yeah, you did. Here we're asked to find the absolute extrema. So if you recall, we need to take the derivative and find the critical numbers. So we're going to have the original function times the derivative of the exponent. Right, so that's my derivative. Now I need to set that equal to 0. So we have 0 equals negative 2x. Now, this has a negative exponent, so I'm going to move that to the denominator and make it a positive exponent. E to the x can never be 0. You might want to go back and look at the original graph of y equals e to the x. Looks like that, has no negative values. Especially if x is then squared, that's always going to be positive, and e is a positive number. So the denominator can't be 0. So the only time this fraction is going to equal to 0 is when the numerator equals to 0, and that's when x would be 0. So that would be your one critical value, and that is in the range that they want us to test the absolute extrema. So now we need to evaluate the function at the endpoints of the interval they give us, along with any critical values that we found. All right, so I'm going to need this to be negative. This is e raised to the negative of negative 1 squared. So that's e to the negative 1, which is 1 over e. This is e to the negative 0 squared, which is e to the 0, which is 1. Anything raised to the power of 0 is always 1. And then here we have e to the negative 1 squared. All right, so those are the same. Then if you want to see what that equals to, punching that into a calculator, this is approximately 0.367, which is definitely smaller than 1. So we have a minimum at, well, when x is negative 1, y is 1 over e. So the minimum value is 1 over e, and the maximum is found when x is 0, y is 1. Okay, on the last problem of your homework, it's a little word problem. And here we go, and it says the percentage of alcohol in a person's bloodstream is given as this. All right, what is the percentage of alcohol in a person's bloodstream after a half hour, after an 8 hour? This is, they give you the percentage. So part A, you're just going to find A of 1/2 by plugging 1/2 in for T, and you're going to plug in 8 for T. You're going to need to have a scientific calculator. You're going to need an E to the X button. That's usually above the button natural log on your calculator. Please find it and practice with it. Now part B, how fast is the percentage of alcohol in a person's changing? So part B, you're going to have to find the derivative first, and then you're going to have to evaluate that derivative at 1/2 and at 8. And again, you will definitely need a calculator.